Hey guys, my name is IBM and I'm still recording quantum physics. This is 9702 physics paper 4, A-level physics. So this is going to be quantum physics lesson. I think it's going to be lesson 3. In lesson 1, we saw the energy of a photon, where we saw that a photon is a quantum or a packet of energy of electromagnetic radiations, where we saw that the energy of a photon was given by hf, and we say that energy was quantized. The energy was existing in small packets which were multiples of hf. That is according to Einstein's quantum theory. Then in lesson 2 we introduced photoelectric emission, and in lesson 3 we want to establish the equation, Einstein's equation of photoelectric emission. Okay, so let's begin by introducing Albert's theory of photoelectric emission that we are going to base on to derive the equation for photoelectric emission. I think it was around 1905 when Albert Einstein developed the theory of quantized energy to explain all the observations associated with photoelectric emission. Albert Einstein proposed that a light radiation or electromagnetic radiation consists of a stream of packets, which we called photons in lesson 1. And when a photon interacts with an electron, the photon transfers all its energy to the electron. That's what we mentioned in lesson 2. That's how we were able to release electrons from the metal surface. So when a photon interacts with an electron, it transfers all its energy to the electron. And when the electron has enough energy, it is able to exit, or it is able to be released from the metal surface. So it is only possible for a single photon to interact with a single electron. In the experiments we discussed in lesson 2, we noticed that the wave theory predicted or suggested that it is possible to eject electrons from the metal surface by shining light for a long period of time, even if light was of low frequency, as long as we would increase maybe the intensity. However, we noticed that even if we increase the intensity, as long as light was of low frequency, it meant that the photons had less energy. They could not knock out electrons. It meant that even if we shine we shine more photons onto the metal surface, the electron does not absorb energy from different photons. It just absorbs energy from a single photon, which energy for this single photon must be high enough to make the electron leave the metal surface. So it is only possible for a single photon to interact with a single electron. The photon cannot share its energy between several electrons. This transfer of energy is instantaneous. It happens immediately. So that's why we never saw a single electron absorbing energy from different photons, and when it becomes enough, the electron would be ejected from the metal surface. That never happened, but that is what the wave theory was predicting. So a single photon gives out all its energy to a single electron. If the energy is not enough to eject an electron from a metal surface, then the electron just undergoes some vibration which warms up the material. But if the energy of the photon is high enough, then that's when the electron would be ejected from the metal surface. So if the frequency of the incident radiation is less than the threshold frequency for the metal, the energy carried by each photon is insufficient to make an electron to escape from the surface of the metal. As long as the frequency is below the threshold, the energy of the photon cannot eject an electron from the metal surface. The electron cannot escape from the attractive forces of the positive metal ions within the material or within the metal. And if the photon energy is insufficient for an electron to escape, this energy is just converted into thermal energy in the metal, because the electrons will lose their kinetic energy to the metal ions when they collide with them. And this is the same reason as to why a metal plate placed near a table lamp gets hot, because the energy from the table lamp is not enough to eject out electrons from the metal plate. the frequency of the light from the table lamp is not enough to cause electrons to be ejected out of the metal surface. Therefore, the energy from the lamp just makes electrons to vibrate within, or just makes electrons to lose their kinetic energy as they collide with other metal ions within the material. So we have noticed two important things here, that a single photon interacts with a single electron. It is a one-to-one interaction. And the frequency of the incident photon must be high enough to cause an electron to be emitted or to be ejected from the metal surface. If the energy is not enough, then this energy is just converted. If the energy of the photon is not enough to knock out electrons from the metal surface, then this energy is just going to be converted to thermal energy in the metal as the atoms of the metal vibrate because of the collision between the free moving electrons within the metal and the metal ions. However, photoelectric emission will not occur. Okay, so therefore, it appears as if there is a minimum energy of electromagnetic radiation which would be required to cause an electron to be ejected from the metal surface. And that minimum energy is going to be called the work function energy. We shall always use the letter phi for the work function energy, and we shall define the work function energy as the minimum energy of electromagnetic radiation required to liberate an electron from the metal surface. Do not forget, we mentioned that the energy of electromagnetic radiation is HF. Because there is a minimum frequency below which a photoelectric emission does not occur, there should also be a minimum energy of an electromagnetic radiation below which photoelectric emission cannot occur. Therefore, the minimum energy of electromagnetic radiation required to liberate an electron from a metal surface is going to be called the work function energy. So we shall not use E for work function energy because we prefer to use E for the general photon energy. Therefore, we shall use phi for the work function energy. The minimum energy of electromagnetic radiation required to liberate an electron or required to release an electron from a metal surface. That's going to be called the work function. This energy is just used. This energy is just used to overcome the nuclear attraction of the electron. That is the nuclear force, to overcome the force of attraction between the electron with the positive nuclei within the metal. And this energy depends on the metal. Because we mentioned in our previous lesson, lesson 2, that different metals have different threshold frequencies. Therefore, different metals will have different work function energies. So this energy, or the work function energy, which depends on the frequency, will also depend on the metal itself. And if the frequency of the incident radiation is equal to the threshold, frequency is just equal to the threshold, that is F equals to F naught. We shall use F naught for the threshold frequency. It means the energy carried by the photon is just sufficient for electrons to, it's just sufficient for electrons at the surface to escape. However, because the frequency of the incident radiation is just equal to the threshold frequency, it means these emitted electrons will not have kinetic energy. There is no surplus for these electrons to be able to move away from the metal surface. They will just stay around the metal surface because they will not have kinetic energy. So, if the frequency of the incident radiation is equal to the threshold frequency, then the energy carried by each photon is just sufficient for electrons at the surface to escape. In other words, the energy emitted by the energy of the photons is equal to the work function, which is going to be h times f naught, where f naught is the threshold frequency. It means the energy of the photon is not giving any kinetic energy to the electrons, but is just setting them free. So they will just be free to escape. However, If the frequency of the incident radiation is now greater than the threshold frequency, in other words, F is greater than F naught, it also means the energy of the photon is greater than the work function, which means when electrons are released, they have a surplus. There is a surplus energy for them to have kinetic energy. So if the frequency of the incident radiation is greater than the threshold frequencies, surface electrons, those are the least tightly held in the metal, they will escape and have surplus energy in the form of kinetic energy. So these electrons will have the maximum kinetic energy and will be the fastest moving electrons. So for the electrons to have kinetic energy, the energy of the photon must be greater than the work function, because the work function is the minimum energy just to set the electrons free. But if the energy of the photon is greater than the work function, then the electrons are set free, and also there is a balance which gives them kinetic energy. There is a surplus for these electrons to have kinetic energy. Then what happens if, here I have considered the tight surface electrons which are least tightly held in the metal. What about if the if the electrons are below the surface, or if the photons penetrate through the metal to eject out electrons that are below the surface? So if a photon interacts with an electron below the surface, some energy is used to take the electron to the surface. Some of the energy of the photon is going to be used to take the electron to the surface and then to set it free, which means more energy is going to be required if the electron is to have more kinetic energy. So if a photon interacts with an electron below the surface, some energy is used to take the electron to the surface so that it is emitted with less maximum kinetic energy. So if you compare an electron which is just on the surface of the metal and compare it with an electron which is below the surface of the metal, if a photon interacts with this electron which is on the surface of the metal, then this electron can easily be released, and therefore it will have a lot of kinetic energy because uh, it experiences less attraction force from the metal ions if it is just on the surface. But for an electron deep below the surface, it will require more energy to bring it to the surface to make it free. That means most of the energy of the photon is used to bring the electron to the surface, which means what remains to give it kinetic energy will be less. So for an electron below the surface, its kinetic energy or its maximum kinetic energy is going to be smaller than for an electron on the surface. So if a photon interacts with an electron below the surface, some energy is used to take the electron to the surface so that it is emitted with less than the maximum kinetic energy. So here the kinetic energy is going to be less because most of the energy is being used to bring the electron to the surface for it to be free. Yet in the first case where we had the electron just on the surface, very less energy is needed to set the electron free. So it means surface electrons have maximum kinetic energy, and electrons below the surface will have energies less than the maximum. What does that imply? Because when photons are incident on the metal surface, they don't discriminate. They interact with both electrons on the surface and electrons below the surface. This will therefore result into electrons on the surface having maximum kinetic energy and electrons below the surface having different energies depending on where they are and depending on how much energy is required to bring them onto the surface. This therefore results into what we call a range of kinetic energies. So electrons will therefore have a range of values of kinetic energy up to some maximum, which we shall be calling Ke max. So the reason as why we have a range of kinetic energies for these electrons is because not all of them reside on the surface. Sometimes photons interact with electrons below the surface, and energy is wasted in bringing the electrons to the surface to set them free, which means the surplus, which is supposed to be given to the electron as kinetic energy, is going to be less than the maximum. It is the surface electrons which have the maximum kinetic energy. So having seen that background, we should now be able to establish Einstein's photoelectric equation. So we mentioned that an electron incident on the metal surface, a photon incident on the metal surface interacts with a single electron. If the energy of the photon is just enough to set the electron free, the electron will not have kinetic energy. The energy is called the work function energy. However, if the photon has excess energy, part of the energy of the photon is going to set the electron free, and the surplus or the balance or the remaining energy will be kinetic energy of this electron. Therefore, the photon energy must be equal to the work function plus the maximum kinetic energy of the photoelectron according to conservation of energy. So Albert Einstein used the principle of conservation of energy to derive what we today call the photoelectric equation. Imagine a single photon interacting with a single surface electron and freeing it or making it free. According to Albert Einstein, the energy of the photon goes into setting the electron free, that is, giving it the work function energy, and the balance will be the maximum kinetic energy of this photoelectron. Remember, the energy of a photon was equal to hf, and we said we shall use the symbol phi for the work function. And also remember, the maximum kinetic energy can be written as Ke max or E max in most cases. Therefore, we shall say that hf, which is the photon energy, equals the work function phi plus the maximum kinetic energy Ke max. Remember, kinetic energy is a half mv squared. Since m is a constant, then it is the v which is going to be changing. So this will be v squared max. So we can write the same equation as hf equals to phi plus a half me v squared max. And this is what we call Einstein's photoelectric equation. So the equation hf equals phi plus a half me, where m is just standing for the mass of the electron, times v squared max, where v squared max is the maximum speed of the electron. This is called Einstein's photoelectric equation. Remember, the work function is equal to h times f naught, where f naught is the threshold frequency. The work function is h f naught, where f naught is the threshold frequency. So that is Einstein's equation. We shall use this equation many times. This equation is not given the list of formula, but when you practice, it becomes part of you. You just need to get it from the conservation of energy. That what is incident on the metal surface is a photon. The photon energy sets the electron free, that is the work function. And the balance of the photon energy is going to be the kinetic energy of the electron. That is, photon energy equals the work function plus the maximum kinetic energy of the photoelectron. So I want you to note that we started with the energy of the photon, which is hf. It is absorbed by an electron. Some of the energy sets the electron free, and we call that the work function. Some of the energy is used in escaping from the metal, setting the electron completely free. That is the work function. And what remains is the kinetic energy which is given to the electron, as simple as that. And by conservation of energy, the energy of the photon should be equal to the work function plus the kinetic energy of the electron. And if the photon is absorbed by an electron that is below the surface, that is underneath the surface, this electron will have kinetic energy less than Ke max. I have already explained that if this is the surface of the metal and the electron is residing below the surface, a photon which is incident and interacting with this electron, it will have, let's say it has 10 joules of energy, which is of course not possible. it will have to waste some joules of energy to bring the electron to the surface. Let's say it loses 6 joules of energy to bring the electron to the surface to set it free. Then it means what remains as kinetic energy will be less than, or it is going to be about 4 joules. But if a photon was interacting with an electron which is just on the surface, if the photon has 10 joules of energy, most probably 1 joule of energy may be used to overcome the force of attraction with the metal ions below the surface, which means this electron would have approximately 9 joules of kinetic energy. So, if the photon is absorbed by an electron that is below the surface, the electron will have less kinetic energy. In fact, it will be less than Ke max. So, electrons ejected from the metal surface therefore have a range of energies, because not all electrons reside on the metal surface. Electrons on the metal surface will have the maximum kinetic energy. For electrons below the metal surface, energy is required to bring them to the surface, which means the kinetic energy of these electrons is going to be below or less than the maximum kinetic energy. I'll use a simple analogy for us to understand this equation. So we are going to picture the electrons as being trapped in what we call an energy well. If you have studied gravitation, you know what we mean by the energy well. Remember, a single photon, as we mentioned, interacts with a single electron to release it. A single photon does not give out its energy to more than one electron, according to the photoelectric theory. So the photon energy must be at least phi. That is, it must be at least the work function. And by this means, Einstein could explain what we mean by the threshold frequency. There is a minimum frequency of electromagnetic radiation which is just enough to eject electrons from the metal surface. So, not all electrons reside on the surface, as demonstrated by this diagram here. So think of a situation where a photon whose energy is hf is incident onto the metal and is just ejecting out an electron from the metal surface. So this electron would escape. But because it was residing on the surface, the energy hf was high enough to set this electron free and also give it some kinetic energy. But then consider the same photon whose energy is hf interacting with an electron which is below the surface. Most of the energy is wasted to overcome the electrostatic forces within the metal ions. Most of the energy is wasted to bring the electron to the metal surface, which means this electron may not have a surplus. It may not have a surplus energy. It may not have kinetic energy. So it just remains around the metal surface. So when a photon arrives at the metal plate, it may be captured by an electron. The electron gains all of the photon's energy and the photon no longer exists. Of course, the photon ceases, the photon disappears. Some of the energy is needed for the electron to just escape from the energy well. The rest is the kinetic energy which is given to the electron. So if the energy of the photon is above the work function, or if the energy is just equal to the work function, then the photon will remain around the surface. The energy is just enough to set the electron free. But if the energy is above, so here in the first diagram here, the energy of the photon is greater than the work function. So the electron is set free and there is a surplus for it to escape to have kinetic energy. Yet here, the energy is just enough to set the electron free. So the energy is just equal to the work function. So the electron will not have kinetic energy. So here kinetic energy is going to be 0. The electron will just remain on the surface. You must have noted the following from what we have just discussed. We can see that the photon model works because it models electromagnetic waves as concentrated packets of energy, each one able to release an electron from the metal. In other words, this model is suggesting that it is a one-to-one interaction. It is disagreeing with the wave theory or the wave model. It's like photons are existing as packets and they are always absorbed as a whole. They are not absorbed in small amounts. So they are packets. They come as a packet of energy. Each one is just able to release an electron from the metal, so it is always absorbed as a whole. The energy of a photon is not shared among electrons. And number two, you must have noticed that a more tightly bound electron, especially those which are below the metal surface, we say they are deep in the energy well, would need more energy to release it from the metal. Otherwise, it just escapes with no energy left for its kinetic energy. If an electron resides below the metal surface, most of the energy is wasted to set it free. Therefore, if it is set free, it may not have enough kinetic energy. But for an electron just on the surface, it is easy to set it free. That means the remaining amount of energy may be high enough to give it the maximum kinetic energy. So I will just give you a summary of some of the rules of photoelectric effect from what we have just discussed. Number one, it's mostly the electrons from the surface of the metal that are removed first in most cases. Electrons from the surface of the metal are the ones which are normally removed during photoelectric effect. Number two, we have already seen that a single photon can only interact and exchange its energy with a single electron. It's a one-to-one interaction. Even though the wave theory was predicting that several photons would give their energy to a single electron, so that when the electron has enough energy, it should be able to escape. That does not happen. Number three, a surface electron is removed instantaneously from the metal surface when the energy of the incident photon is greater than or equal to the work function. As long as the frequency of the incident radiation is above threshold, as soon as the radiation is incident on the metal surface, an electron is ejected. So the emission is instantaneous. There is no time delay between illumination and emission. There is no time delay between illumination and emission as long as the frequency of the incident radiation is above threshold. Because if the frequency is above threshold, then the energy is above work function. And number four, we have already seen that energy must be conserved when a photon interacts with an electron. That's why the energy of the photon set the electron free and part of it became kinetic energy. That is, photon energy equals the work function plus the maximum kinetic energy of the electron. However, if we increase the intensity, increasing the intensity of the incident radiation does not release a single electron when its frequency is less than the threshold frequency. Even though the wave theory was predicting that you could make the light brighter, in other words, you could increase the intensity or you could increase the number of photons, even though their frequency was less than the threshold. But observations showed that even if you increase the intensity, as long as the frequency is less than the threshold, not even a single electron would be released from the metal surface. The intensity of the incident radiation is just proportional to the rate at which photons arrive at the plate, but each photon still has energy less than the work function. So when you increase the intensity, you're just increasing the number of photons incident with the metal surface per unit time. You're just increasing the rate at which photons arrive at the plate or at the metal surface per unit time. But these photons still don't have enough energy to eject electrons out of the metal surface. However, if the frequency was to be above the threshold, then increasing the intensity would mean that more photons are arriving on the metal surface per unit time, which would mean more electrons would be ejected. So intensity affects the rate of emission of electrons as long as the frequency of the incident radiation is above the threshold. The intensity only affects the rate of emission as long as the frequency of the incident radiation is above the threshold. Points to note. So we have already seen that for radiation incident at a threshold frequency f naught, that is the minimum frequency, the electron is released from the surface, but this electron will not have enough kinetic energy. In other words, according to the photoelectric equation, the energy of the photon is just enough to set the electron free. So it means the energy of the photon is just going to become the work function. So hf naught is equal to phi, because the frequency of the incident radiation is hf. So the energy of the photon, which would be hf, is going to be hf naught. So this energy is just enough to set the electron free, but not to give it kinetic energy. So half me v squared max is going to be 0. Remember from general wave properties, or from waves, the speed is equal to lambda times f. So it means c is equal to lambda naught f naught. F naught can be c over lambda. So the work function can also be given as hc over lambda naught. Of course, we know that c is the speed of light because we are dealing with photons, or we are dealing with electromagnetic radiation. So c is the speed of light, which is 3 times 10 to the power of 8. 3 times 10 to the power of 8 meters per second. Now lambda naught is going to be called the threshold wavelength. So we have seen threshold frequency, and now we are talking about threshold wavelength. Note that different metals have different frequencies. They have different work functions. They have different threshold frequencies. They will also have different threshold wavelengths. So different materials or different metals have different threshold frequencies, and hence they will have different work functions. They will have different threshold wavelengths. For example, if you think about alkali metals like sodium and potassium, these ones have threshold frequencies in the visible region, which means if I shine a visual light onto an alkali metal such as sodium or potassium, electrons will be ejected. But if I shine visible light onto a zinc plate, there were no electrons ejected. So different metals have different threshold frequencies. The alkali metals like sodium, electrons could be ejected from their surfaces if visible light is shined onto the metal surface. The conduction electrons in zinc are more tightly bound within the metal, and so its threshold is in the ultraviolet region. So to eject electrons from the metal surface of zinc, we need ultraviolet light, or light in the ultraviolet region and above. So it means different metals will have different threshold frequencies. They will therefore have different threshold wavelengths. They have different work function energies. Okay, so therefore the photoelectric equation can be written as, or it has already been written as, HF equals to phi plus a half me v squared max. We are now familiar with that equation. Remember in lesson 2, we saw the stopping potential. So we saw that kinetic energy of the electrons determined the stopping potential, and therefore a half mv squared max is equal to E times Vs, where Vs is the stopping potential. So when I substitute for the kinetic energy with EVs, it means I could write the photoelectric equation as HF equals to phi plus EVS, where EVS is the stopping potential. EVS is the stopping potential. If I try to make VS the subject in that equation, VS would be equal to HF over E minus phi, HF over E minus phi over E, which means if I decide to sketch a graph of maybe stopping potential against the frequency, remember we saw that it is the frequency which affected the stopping potential, which determined the stopping potential. It wasn't the intensity. So if I was to sketch stopping potential against frequency, you notice that this graph has an intercept which is negative. So there should be an intercept down here, which is going to be phi divided by E. And when the stopping potential is zero, you notice that HF is going to be equal to, when the stopping potential is zero, when I make this to be zero, it means that HF is going to be equal to phi. So this frequency here is going to be the threshold. So there is an x-intercept somewhere here. So this means it will be a straight, it is going to be a straight line like that most of the times. So the graph is always going to be the same shape. So a graph of stopping potential against a frequency can be obtained from that equation, and the graph would always take that shape. And from the graph of stopping potential against a frequency, where the graph crosses the x-axis, in other words, where the stopping potential is zero, it means the energy was just enough to set the electron free, but not to give it kinetic energy. So it means HF is equal to phi, where F is going to be F naught, which is going to be called the work function, the threshold frequency. So from the graph, we can determine the Planck's constant. From this equation, when you compare this with y equals to mx plus c. On the y-axis, I have the stopping potential. On the x-axis, I have frequency. So you notice that the gradient is going to be h over e. So the gradient is going to be h over e, which means I can find the gradient. I can find Planck's constant by multiplying the gradient times the charge of the electron. Then, if I take this further downwards, you notice that the y-intercept is phi over e, and of course it is negative. So to obtain the work function, the y-intercept c is obtained. And you notice from the graph that the y-intercept equals to phi over e, which implies that phi is the intercept times e. So the work function will be the y-intercept times e. The work function will be the y-intercept times e. Okay, so when you check on the solved past paper questions, which I have already solved, you'll see most of these graphs and they have almost the same shape. Note: so experimental evidence indicates that photoelectric current, when I talk about photoelectric current, remember current is the rate of flow of charge carriers. In this case, photoelectric current, the electrons have been ejected by illuminating a metal surface with electromagnetic radiations of high enough frequency. So experimental evidence indicates that the photocurrent, that is the rate of emission of photoelectrons, depends on the intensity of the radiation, as long as, of course, when the frequency is constant but above threshold. So photocurrent is directly proportional to the rate of emission of photoelectrons depends on the intensity, as long as the frequency is above threshold but constant. So it means increasing the intensity will give rise to increasing rate of emission of photoelectrons. The higher the intensity, the higher the photoelectrons emitted from the metal surface. But remember, this is only true if the incident radiation has high enough frequency. This observation has led many students to believe that a rate of emission is independent of the frequency, but this is incorrect. We have kept the frequency constant. In fact, a beam of radiation has an intensity. A beam of electromagnetic radiation has an intensity. And from your AS physics, intensity is equal to the power per unit area of the surface. Intensity equals to the power over area. And since power is energy over time, so this is energy, I'll just use total energy over T then times area. But because we are considering electromagnetic radiations, where electromagnetic radiation could be made up of several photons, so it means the intensity is going to be equal to, remember the energy of a single photon is hf, so this is going to be total number of photons times the energy of each photon, then this is divided by T divided by area. So the intensity is equal to NT hf over A. So intensity is equal to the power per unit area of the surface. And since the beam consists of a stream of photons, the intensity is the product of the rate of arrival of photons, which is n over t, that is the rate of arrival of photons, and the energy of each photon, which is hf. The rate of arrival of photons on a given area times the energy of each photon, which is hf. So this means frequency affects the rate of emission if it is not kept constant. So if we keep the intensity constant instead, of course we can't keep intensity constant and the frequency constant at the same time, because Planck's constant will be a constant and A is going to be a constant. So at constant intensity, it means the rate at which photons arrive at the metal surface depends on the energy of the photon. So if I keep the intensity constant, it therefore means N over T is going to be equal to I times A divided by HF. The rate at which photons arrive at the surface, if the intensity is constant, of course the area is constant, Planck's constant is constant, the number of photons that are arriving at the surface per unit time is going to therefore be depending on the frequency. So if the frequency increases, it means the energy of each photon has increased. Therefore, only a few electrons can arrive at a given surface per unit time. That is, the rate of arrival of photons on the surface decreases. If the frequency decreases, it means the energy of the photons has decreased, which means the rate of arrival of photons on the given surface increases. So, at constant intensity, the rate at which photons arrive at the metal surface depends on the energy of each photon. If the frequency of the radiation increases, it means the energy of the photon has increased, because the energy of a photon is hf. So when F increases, it means the energy has increased. And if the frequency is constant, of course the area is constant, it means the rate of arrival of photons must decrease. That is, the number of photons per unit time arriving on the area, on a given area, must decrease, which therefore implies fewer photons per unit time are going to be arriving on the surface, and fewer photons per unit time means a smaller rate of emission of electrons, hence a smaller photocurrent. So, increasing the frequency at a constant intensity decreases the rate of arrival of photons on the metal surface. In other words, fewer photons arrive on the metal surface, which means because each photon ejects a single electron, it means fewer electrons are going to be ejected from the metal surface. And if fewer electrons are ejected from the metal surface, we say a smaller photocurrent is emitted, because it is these ejected electrons that constitute the photocurrent. So, it's wrong to think that the frequency, that the rate of emission is independent of the frequency. If the frequency is not kept constant, then the rate of emission is going to also depend on the frequency of the incident radiation, because at constant intensity, increasing the frequency means that the photon energy has increased. And from this mathematical expression that I have used here, n over t is the number of photons arriving on the surface per unit time. I just made n over t the subject. And if frequency is increased, photon energy is increased, it means fewer photons can arrive on the given surface per unit time. That means fewer electrons can be ejected from the metal surface, and therefore we say the photocurrent decreases. To sum this up, I will just give the definitions of the terms we have been using here. One, we have been talking about the threshold frequency. So this is the minimum. You should be referring to the minimum. The minimum frequency of electromagnetic radiation that could emit photoelectrons from a material when the material is being irradiated. In other words, it is the minimum frequency below which no photoelectric emission can occur. The minimum frequency of the incident electromagnetic radiation, below which photoelectric emission cannot occur. Many times my students forget to refer to minimum frequency, or if they refer to the minimum frequency, they may forget to refer to electromagnetic radiation or photons. So the minimum energy, the minimum frequency of a photon below which photoelectric emission cannot occur, the minimum frequency of the incident electromagnetic radiation below which photoelectric emission cannot occur. Because C equals lambda times F, if this is lambda naught and this is F naught, if F naught is the minimum, then lambda naught is going to be the maximum, because wavelength and frequency are inversely proportional. Therefore, the threshold wavelength is going to be the maximum wavelength of the incident radiation, because for threshold frequency was below which, then this is going to be above which photoelectric emission cannot occur. So there is a frequency below which photoelectric emission cannot occur, which means there is a wavelength above which photoelectric emission cannot occur. You should be able to define a threshold frequency and threshold wavelength. Threshold wavelength is the maximum wavelength of the incident radiation above which photoelectric emission cannot occur. I think we now qualify to do some examples. I will do a few examples. I may not do all of them because they're almost the same. Example 1, you can pick your book and try to solve these examples. You can always pause the video and use your knowledge or your understanding to solve the question and see if you would get the same answer as the one quoted in the question or the one which I would get. What is the maximum kinetic energy of photoelectrons ejected from magnesium when irradiated by an ultraviolet light of frequency 1.5 times 10 to the power of 15 Hertz? What is the maximum kinetic energy of a photoelectron ejected from magnesium when it is irradiated by an ultraviolet light of frequency 1.5? Okay, so I'll just use the top part. For you have a book, I don't have a book here. So photon energy E is equal to H times F, and photon energy is H times F, but we said the energy of a photon, which is HF, equals to the work function, which is phi, plus the maximum kinetic energy. I'll just call it Emax. So this means that the maximum kinetic energy Emax is going to be equal to HF minus the work function, which is phi. So they have given us the work function as 5.9 times 10 to the power of minus 19 joules. They have given us the frequency, so I'll just say this is equal to Planck's constant is 6.63 times 10 to the power of minus 34, then times the frequency, which is 1.5, times 10 to the power of 15, then minus the work function, which is 5.9 times 10 to the power of negative 19. So I'll check with my calculator. 6.63 exponent minus 34 times 1.5 exponent 15, then minus 5.9 exponent minus 19. So this is giving me 4.045, which is approximately 4.04 or 4.0 times 10 to the power of minus 19. So this answer is correct. A conductor has a threshold wavelength 0.85 micrometers. Calculate its threshold frequency. So from C equals to lambda times F, so it means C is going to be lambda naught times F naught. So this means threshold frequency is going to be C, which is 3 times 10 to the power of 8, divided by threshold wavelength, which is 0.85 micro is 10 to the power of minus 6. So I will check my calculator. 3 exponent 8 divided by 0.85 exponent minus 6. So this is 3.53 times 10 to the power of 14 hertz. So this answer is correct. Then the work function phi in electron volts. Work function phi. So phi can be equal to H F naught. Since I have F naught, I'll just say 6.63 times 10 to the power of minus 34 times F naught, which is 3.53. Remember, F naught is the threshold frequency. So that is 3.53 times 10 to the power of 14. Then I check with my calculator. So this is 2.34 times 10 to the power of minus 19. I just used the answer which was in the calculator. Then this is in joules, so but they want the answer in electron volts, so we have to divide this by 1.6 times 10 to the power of minus 19 to change it to electron volts. So divide this by 1.6 exponent minus 19, which is 1.46 electron volts. So this answer is correct. Then the maximum speed of the photoelectrons emitted when the conductor is irradiated by a blue light of wavelength 0.49. I've remembered one student said they don't see red, so sorry for that. The maximum speed of the photoelectrons emitted when the conductor is irradiated by a blue light of wavelength 0.49 micrometers. Okay, so we want to find the maximum speed. So it means we can find the maximum kinetic energy first. So energy of a photon HF is equal to the work function plus the maximum kinetic energy, which is a half m v squared max. So this is going to be, I will just substitute into this equation, making V max the subject. So V max is going to be the square root of, that is going to be HF minus phi, then times 2. So it becomes 2 into HF minus phi, then divide by the mass. I've just made V max the subject, so I'll just substitute in my square root. So that would be 2 into 6.63 times 10 to the power of minus 34 Then I'll put this outside. So then times F. F, they have given us the wavelength. Of course, we know that F equals to C over wavelength. So I will say C is 3 times 10 to the power of 8 divided by the wavelength. The wavelength is 0.49 times 10 to the power of minus 6. This is F. Then minus the work function. Of course, the work function has not changed. It is 2 point. This is what I got as the work function in joules. So because these are all in SI, so this should also be in joules. So this is going to be minus 2.34 times 10 to the power of minus 19. Then I will subtract this. Then I will divide by the mass of the electron, which is 9.11 or 9.1 times 10 to the power of minus 31. So I'll use my calculator at once. So I have 6.63 exponent minus 34 times 3 exponent 8 divided by 0.49 exponent minus 6. Then I subtract the work function, 2.34 exponent minus 19. Then I multiply by 2. I divide by the mass, 9.11 exponent minus 31. Then I find the square root. So this is giving me 6.14 times 10 to the power of 1, 2, 3, 4, 5. So it means this answer is correct. Okay. In a photoelectric experiment, a beam of light of wavelength 700 nanometers. So the wavelength is 700 nanometers, is incident on a metal when the stopping potential is negative 1.5 volts. No current is obtained. Calculate the work function phi of the metal. So they have given us the stopping potential, they have given us the wavelength, and they have said when the stopping potential is negative 1.5 volts, no current is obtained. So remember, the energy of a photon, which is given as HF, is equal to the work function plus the kinetic energy, which I will call Ke max. But also, I want you to remember that maximum kinetic energy was also equal to the maximum kinetic energy was also equal to the charge of the electron times the stopping potential EVS. So it means I can say HF equals the work function plus EVS. Okay, so when you make the work function the subject, then it means the work function is going to be equal to HF. Because they gave us the wavelength, I will remove F and I put C over lambda, so this is going to be HC over lambda, then minus E times Vs. So I'll just substitute here. So the work function phi is going to be equal to Hc, that is 6.63 times 10 to the power of minus 34 times C, which is 3 times 10 to the power of 8, divided by the wavelength, which is 700 times 10 to the power of minus 9. Then I subtract the charge of the electron, which is 1.6 times 10 to the power of minus 19, then times the electric potential. Of course, if the stopping potential is minus 1.5, then I'll just take the potential difference, which is 1.5. Of course, I know students will put the negative, which will cancel out this one here, but it's not necessary. If the stopping potential is minus 1.5, then the potential difference is going to be 1.5. So I'll just press my calculator. Okay, so from my calculator, I'm getting 4.4 times 10 to the power of minus 20 in joules. So this answer is correct. The work function of platinum is 9.0 times 10 to the power of minus 19 joules. Calculate the threshold frequency for the emission of photoelectrons from platinum. So threshold frequency phi equals to h times f naught. I will not calculate that. They've given us the work function. We know what h is. We just make f naught the subject. The maximum kinetic energy of the photoelectron when radiation of the frequency 2.0 times 10 to the power of 15 hertz is incident on platinum surface. So we know that the energy of the photon hf equals to the work function plus the maximum kinetic energy, which I'll call Emax. So it means the maximum kinetic energy, Emax, is simply going to be the work function, which was given as, it's the energy of a photon, which is going to be h, that is 6.63 times 10 to the power of minus 34 times the frequency, which is 2 times 10 to the power of 15, then minus the work function. So the work function is 9.0 times 10 to the power of minus 19. I'll just check if this answer is correct. Yeah, this is correct. You can also check. Light of frequency 6 times 10 to the power of minus 14 hertz is incident on a metal surface, and the emitted electrons have kinetic energy 2 times 10 to the power of minus 29 joules. Calculate the work function. So this is the kinetic energy. This is the incident frequency. So the work function phi equals the energy of the photon hf minus the kinetic energy Emax. I just modify the equation, so you just substitute. So this is going to be equal to h is 6.63 times 10 to the power of minus 34, then times the frequency, which is 6.0 times 10 to the power of minus 14. I don't think this is minus 14 because that frequency would not exist. I think that is positive 14. That is positive 14. Okay, so this is HF, then minus Emax. The kinetic energy is 2 times 10 to the power of minus 29. Okay, so I'll just check my calculator. 6.63 exponent minus 34, then times 6 exponent 14, then minus 2 exponent minus 29. So this answer is correct. Then so that is the work function. Then the threshold frequency. Of course, the work function is equal to Planck's constant times the threshold frequency. So I just divide the work function by h. I'll just divide that by h is 6.63 exponent minus 34. So this one is correct. Threshold frequency. So 6 times 10 to the power 14 is the threshold frequency. Okay. The graph below shows how the maximum kinetic energy of the photoelectrons varies with the frequency f of the ultraviolet light that falls on metal A. So we have metal A here, and it is of course a straight line. Which aspect of the graph could not be explained with the wave model of light? Of course, we noticed that the wave model of light could not explain why the maximum kinetic energy of photoelectrons depends on the light frequency. The wave model did not explain why kinetic energy is directly proportional to the frequency. It could not explain why we have this minimum threshold frequency below which no photoelectrons are emitted, irrespective of the intensity of the light. It could not explain why the photoelectrons can still be emitted instantaneously when light of very low intensity was used, as long as the light was having frequency above the threshold. So the wave theory failed in almost three things. It did not explain why kinetic energy depends on frequency, threshold on the light frequency, why there is a minimum frequency, which we call the threshold, and why emission is instantaneous, even with light of low intensity. Then state the threshold frequency f naught, and hence or otherwise determine the work function. So from the graph here, you see the threshold frequency here is 1.5 times 10 to the power of 15 hertz, and hence work function. So the work function is h times threshold frequency. So I'll just multiply the Planck's constant by the threshold frequency. So Planck's constant is 6.63 times 10 to the power of minus 34, then times 1.5 times 10 to the power of 15. So this is 9.9, which is the same as approximately 10. 9.95 times 10 to the power of minus 19 joules, which is approximately 10. Okay, then so that is the work function. Then use the above to calculate the value of Planck's constant. So use the graph above to calculate the value of the Planck's constant. So here I used h, but perhaps I was not supposed to use h in this question, because there is no way the next question will ask me to determine the value of Planck's constant, yet I've already used it to calculate the work function. So alternatively, I could find the work function from the graph directly by just extrapolating this here. And you notice that work function, okay, HF equals the work function plus Emax, and when Emax is 0, H times F equals the work function, and also when I'm looking for a point where F is 0. When this is 0, the phi equals to the negative Emax, or Emax equals to the negative phi. When HF is 0, that is at this point here. So it means I can just take this as the work function. I will not take the one which I have calculated because the next part asks me to find the work function. So energy of a photon equals the work function plus the maximum kinetic energy. And when this part is when this part is 0, it means Emax, or the work function, equals the negative of Emax, which is negative 10. So this is going to be negative of negative 10 times 10 to the power of minus 19, which is actually going to be 10 times 10 to the power of minus 19. Our calculation, we had got 9.95. So this is the work function. I could read it from here, but from this equation, when the frequency is 0, in other words, I just take the y-intercept. The y-intercept is a graph of Emax equals to hf minus phi, compare with y equals to mx plus c. So it means negative phi equals to the y-intercept. But of course, the y-intercept is negative, so the negative cancels, so it becomes a positive. Then use the above graph to calculate the value of Planck's constant. So one, of course, we can find Planck's constant from the gradient. For example, you notice that if I have a graph of Emax equals hf minus phi, the gradient is going to be the Planck's constant. So h equals to the gradient. H is going to be equal to the gradient. So I don't have clear lines here, but so I'll just approximate this. So this is going to be 10 minus 0. Of course, this is times 10 to the power of minus 19 on the y-axis. On the x-axis, I have 3 minus 1.5. This is times 10 to the power of 15. So this is giving me 6.7 times 10 to the power of minus 34 joule seconds. I think this is very close to 6.63 times 10 to the power of minus 34. As long as the power of 10 is still minus 34 and the first digit is 6 point, then I think that is fine. Okay. What is the stopping potential Vs? What is the stopping potential Vs when ultraviolet light of frequency 3 times 10 to the power of 15 Hertz irradiates on metal A? So what is the stopping potential? So from the graph, when frequency is 3.0 times 10 to the power of 15, the maximum kinetic energy is 10. I've just drawn this line here. So we want to find the stopping potential. And remember, kinetic energy, half mv squared was equal to E times the stopping potential Vs. So when the frequency 3.0 times 10 to the power of 15 as given in the question, the kinetic energy is 10 times 10 to the power of minus 19. So from that, I'm going to find the stopping potential. So we shall have that E times the stopping potential is equal to E max, or maximum kinetic energy, which means the stopping potential Vs is going to be 10 times 10 to the power of minus 19. We divide this by the charge of an electron, 1.6 times 10 to the power of minus 19. So this is about 6.25 volts. Using the same axis above, sketch a line to represent the variation of maximum kinetic energy, Kmax, with frequency f for a metal with a larger work function. So if the metal has a larger work function, the only difference is going to, remember, Planck's constant is a constant. Phi is equal to h times f naught. This is a constant for all the materials. So if the work function is bigger, the threshold frequency is bigger. Because h is a constant, it means these lines are always parallel to each other. They should have always the same gradient. The lines always have the same gradient. So it only has a higher work function. So if I go back to this, so because it had a higher work function, it makes sense to say that the graph has a higher work function. I mean, it has a higher threshold frequency, as you can see demonstrated by this letter B. So I think that makes sense. Okay, so I even gave here the answers. The wave mode of light could not explain why the maximum kinetic energy of the photoelectrons depends on the light frequency. Why kinetic energy is directly proportional to the light frequency. It could not explain the existence of the threshold frequency, below which no photoelectrons are emitted, irrespective of the intensity of light. It also could not explain why these photoelectrons can still be emitted instantaneously when light of very low intensity was used, as long as the frequency is above the threshold. So the wave theory did not account for that. We saw, I think, we saw the work function, we saw the Planck's constant, and we calculated the stopping potential. And we have also seen the graph labeled B for greater work function means a greater threshold frequency. So the line is supposed to be on the right hand side of the line, which was labeled A. Because h is a constant and h is the gradient, the lines have the same gradient. They are parallel to each other, but the other one has just a higher threshold frequency. Okay. Calculate the maximum speed of electrons. Calculate the maximum speed of photoelectrons emitted by a cesium surface when irradiated with light of wavelength 484 nanometers if the work function is 3 times 10 to the power of minus 19. So do not forget the work function. I mean, the energy of a photon h phi is equal to the work function phi. Hf is equal to phi plus the maximum kinetic energy. I'll just write E max. And do not also forget that kinetic energy is a half mv squared. And also F is lambda. F is C over lambda. So I'll just make, let me just substitute into the equation. H is 6.63 times 10 to the power of minus 34. Then F is C over lambda, so that is 3 times 10 to the power of 8 divided by the wavelength, which is 484 times 10 to the power of minus 9, that is HF, should be equal to the work function. The work function has been given as 3 times 10 to the power of minus 19 plus kinetic energy is a half mv squared, so I'll say it is a half. The mass of the electron is 9.11 times 10 to the power of minus 31, then times v squared. So I'll just press my calculator to get v. So from my calculator, I think this is very correct. Then a photoemissive metal has a threshold wavelength of 0.45 micrometers. Calculate the kinetic energy. Calculate the kinetic energy of the electrons when light of wavelength 0.35 micrometers falls on the metal. So the threshold wavelength is that, and we want to find the kinetic energy. So remember, I think I should use this. Should I employ this space first? So I'm employing this space first. So energy of a photon is hf. This should be called the work function phi plus the maximum kinetic energy, which is a half. I'll just write Emax because we don't want speed, we just want kinetic energy, Emax. But they have given us threshold wavelength. So I must modify this equation to bring in wavelength. That means where there is F, I'll put hc over wavelength. Where there is work function, I'll put hc over lambda naught because work function is h f naught and f naught is c over lambda naught. Then plus the maximum kinetic energy, Emax. So if I substitute, I'm just going to substitute and find Emax straight away. So on the left hand side, I have 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by the wavelength of the photon, which is 0.35 times 10 to the power of minus 6. On the right hand side, I have 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by the threshold wavelength, which is 0.45 times 10 to the power of minus 6. This is plus Emax. So I'll just simplify the left minus the work function. So from my calculator, Emax, which is the maximum kinetic energy, is going to be 1.26 times 10 to the power of minus 19 joules. A copper surface is irradiated by light of wavelength 2.5 times 10 to the power of minus 7 meters and has a stopping potential of 0.25. Calculate the work function. So they have given us the wavelength of light and they have given us the stopping potential. So we just need an equation which has stopping potential, such as, I think I should use the space at the bottom, but before I can write here, energy of a photon, HF, is equal to the work function plus the kinetic energy. Remember, the kinetic energy is also equal to the charge of the electron times the stopping potential. So the question is calculate the work function. So the work function phi is going to be equal to the energy of the photon HF. Since they gave us wavelength, HF is going to be 6.63 times 10 to the power of minus 34. Because F is C over lambda, so I'll say times 3 times 10 to the power of 8, that is for C, divided by the wavelength, which is 2.5 times 10 to the power of minus 7. Then I subtract, because I'm making phi the subject in that equation. So minus E, which is 1.6 times 10 to the power of minus 19 times the stopping potential, which is 0.25. So I'll press my calculator and check. So this is giving me 7.6 times 10 to the power of minus 19 joules. So this answer is correct. The maximum kinetic energy of photoelectrons ejected from a tungsten surface by monochromatic light of wavelength 248 nanometers was found to be 8.0 times 10 to the power of minus 20 joules. Find the work function. Okay, I'll just clear this space first. Okay, find the work function. So they have given us the wavelength as that, and they have given us the maximum kinetic energy as being that. So the energy of a photon equals the work function plus the maximum kinetic energy. So because I want to find the work function, they've given us wave frequency is equal to C over lambda. So the work function phi is going to be hc over wavelength minus the maximum kinetic energy. So this is going to be 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by the wavelength, which is 248 times 10 to the power of minus 9. Then I'm subtract this, that is minus Emax, which is 8.0 times 10 to the power of minus 20. Okay, so this is giving me find the work function for tungsten. So this is giving me 7.1 times 10 to the power of minus 19 joules. You can also verify that. Sodium has a work function of 2.3 electron volts. Calculate the threshold frequency, stopping potential when illuminated by light of wavelength 5.5 times 10 to the power of minus 7 meters. 1 electron volt is 1.6 times 10 to the power of minus 19 joules. So they have given us the work function and they have given us the frequency. They want us to find the threshold frequency. So we know that work function equals to H times the threshold frequency. So it means the threshold frequency F naught is going to be the work function, which is 2.3 times 1.6 times 10 to the power of minus 19. Divide this by Planck's constant, which is 6.63 times 10 to the power of minus 34. I'll just press my calculator. 2.3 exponent, so times 1.6 exponent minus 19. Divide by 6.63 exponent minus 34. So this answer is correct. Then part B, stopping potential when illuminated by light. So we know that energy of a photon, which is HF, is equal to the work function plus the maximum kinetic energy. But remember, kinetic energy is equal to E times the Vs. So it means HF equals to the phi plus E times Vs. So to find the stopping potential Vs, I'm just going to find H times F, which is 6.63 times 10 to the power of minus 34 times F. They gave us a wavelength, so F is C over lambda. So I'll just say times C, which is 3 times 10 to the power of 8, divided by the wavelength, which is 5 times 10 to the power of minus 7, then minus phi, which phi is 2.3 times 1.6 times 10 to the power of minus 19. That is phi. Then I'm going to divide the whole of this by E because I was making stopping potential the subject. So divide by 1.6 times 10 to the power of minus 19. Okay, I'll press my calculator. 6.63 exponent minus 34 times 3 exponent 8 divided by 5 exponent minus 7, then minus 2.3 times 1.6 exponent minus 19, then divide by 1.6 exponent minus 19. So this is giving me 0.18625, which means this answer is correct. Then calculate the maximum velocity of the electrons produced when sodium is illuminated by light of that wavelength. So of course we know that a half m v squared is equal to E times Vs. So that means the speed V is going to be 2 times the charge of the electron 1.6 times 10 to the power of minus 19 times the stopping potential, which is 0.186. Then divide this by the mass, which is 9.11 times 10 to the power of minus 31 under the square root. That gives us the speed. So I'll check this. Times 1.6 exponent minus 19 times 2. Divide by 9.11 exponent minus 31 under square root. So this is 2.56. So this answer is correct. You can also verify. Last example, when light of wavelength 5.9 times 10 to the power of minus 7 is incident on a sodium metal, electrons of maximum kinetic energy, that is 1.71 times 10 to the power of minus 20, are emitted. Calculate the maximum kinetic energy of the electrons that will be emitted by the sodium metal, I think. Calculate the maximum energy of the electrons that will be emitted by the sodium metal. illuminated by light of wavelength 4.5 times 10 to the power of minus 7 meters. Okay. So first of all, we must be able to use the general equation. I will need the whole of this space, I think. So I'm going to use the whole space on this page. So we know that energy of a photon, which is h times f, is equal to the work function plus the maximum kinetic energy. So this is going to be plus Emax. So the question is, calculate the maximum kinetic energy of the electrons that will be emitted by the sodium metal illuminated by light of wavelength 4.5 times. When light of wavelength 5.9 times 10 to the power of minus 7 meters is incident on the sodium metal, electrons of maximum kinetic energy 1.71 are emitted. So this is going to help us to get the work function, because we have the wavelength, we have the incident, the kinetic energy. The work function is a constant for the same metal. So I'll simply say the work function F phi is going to be equal to, remember F is C over lambda. So it's going to be H, which is 6.63 times 10 to the power of minus 34 times C over lambda, which is going to be 3 times 10 to the power of 8, divided by the wavelength, which is 5.9 times 10 to the power of minus 7. Then minus the kinetic energy, which is 1.71 times 10 to the power of minus 20. So this is going to be a constant for the same sodium metal. So I'll press my calculator. So that is 6.63 exponent minus 34 times 3 exponent 8 divided by 5.9 exponent minus 7. Then I subtract the kinetic energy, so minus 1.71 exponent minus 20. So the work function is 3.2 times 10 to the power of minus 19 joules. So it is the work function for the same metal. Now we're going to change the wavelength to this one. So calculate the maximum kinetic energy. So from this equation here, maximum kinetic energy is HF minus the work function. So Emax is going to be HF minus the work function, so which is going to be 6.63 times 10 to the power of minus 34. Because they gave us wavelength, F is C over lambda, so that is 3 times 10 to the power of 8, divided by the wavelength, which is 4.5 times 10 to the power of minus 7. Then minus the work function, which we have got as 3.2 times 10 to the power of minus 19. So I have that 6.63 exponent minus 34 times 3 exponent 8 divided by 4.5 exponent minus 7, then minus 3.2 exponent minus 19. So this is going to be equal to 1.22 times 10 to the power of minus 19 joules. If you want to change it to electron volts, you just divide this by 1.6. Divide this by 1.6 times 10 to the power of minus 19, which I think is 1.22 divided by 1.6. That's 0.625 electron volts. So I think this is correct. So you now qualify for a self-check. There are several self-check questions for you. You just pause the video and try to answer the self-check. So most of these I will not give a hint, they are direct questions. These are direct questions. Most of them I've given an example similar to those to the questions in the self-check, so I don't expect anyone to find challenges with these. These are very, just remember that 1 electron volt is the same as 1.6 times 10 to the power of minus 19 joules. To change from electron volts to joules, you multiply, and change from joules to electron volts, you divide by 1.6 times 10 to the power of minus 19. So you should be able to answer the self-check questions on this slide. You should also be able to answer the self-check questions on this slide. For practice, you can plot a graph. Plot the graph of these results to find Planck's constant. Of course, if you plot energy against frequency, I expect you to have such a straight line. And Planck's constant is the gradient. The cutoff frequency is the threshold frequency. The work function from the graph, you notice that when f is 0, the work function phi is going to be equal to the negative of the maximum kinetic energy. So just read the value from the graph. These are approximate values. Show that energy of a photon whose wavelength lambda in nanometer is given by that. I will just show this. So energy is equal to h times f, which is hc divided by wavelength, which is going to be 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by lambda. So this one is this is going to be in meters. So this, because these are NSI units, this one is in meters. So if it is in nanometers, to change wavelength from meters to nanometers, I have to divide by 10 to the power of minus 19. So when I divide it, the 10 to the power of minus 9 goes up. So this is going to be the same as 6.63 times 10 to the power of minus 34, then times the 3 times 10 to the power of 8, divided by lambda. If lambda is in nanometers, I have to multiply here by 10 to the power of minus 9, because if the wavelength is in meters and we are to change it into nanometers, I divide by 10. So when I say x by 10 to the power of minus 9 to change to nanometers, so it means the 10 to the power of minus 9 goes up. Then this would be in joules, but we want it in electron volts, so I have to divide this by 1.6 times 10 to the power of negative 19. Let me check this. 6.63 exponent minus 34 times 3 exponent 8 times 1 exponent minus 9 divided by 1.6 exponent minus 19. No, I think I don't need to convert this. (6.63 exponent minus 34 times 3 exponent 8 divided by 1.6 exponent minus 19. because the wavelength was in nanometers, so I have to change this. So I have to change this to times 10 to the power of minus 9 to change it to meters. Okay, so this is going to be 1243 divided by lambda electron volts, which I think is that. Okay, so you can try the other questions. I've given several examples for these. You can also try this one. You can try this one. You can always pause the video and try the examples. Data for the threshold for F naught and work function energy phi for some metals are shown to capture the threshold frequency for platinum. So just use they've given the work function. You should be able to just use phi equals to h times F naught. Determine which metals will emit photoelectrons. Of course, those metals whose whose energy is greater than the work function should be able to emit electrons, or whose when the incident radiation is having frequency above the threshold, then those metals should be able to emit photoelectrons. So you have to check. Either you check the energy for this wavelength and a beam of electromagnetic radiation having continuous range of wavelengths between this and this. So we'll get this range of energies, or you can check the threshold wavelengths. If the frequency is greater than the threshold, you can get this frequency and see. If the frequency is greater than the threshold, then photons are emitted. Or you check the wavelength should be less than lambda naught. If the wavelength is less than the threshold wavelength, then it means photons are emitted. Or the energy of the photon should be greater than the work function. So you have three methods. You can check their frequencies. For example, I'll just check the last one. Okay, let me just calculate this. 320 and 350, that is the range of the wavelengths of the incident radiation. Then let's check what is this threshold wavelength here. Here the threshold wavelength is going to be, remember, F is equal to C over lambda, which means lambda is equal to C over wavelength. I mean C over F. So here it is going to be 3 exponent 8 divided by 8.8 exponent 14. When I change it to nano, so I'll say divide by 1 exponent minus 9. So this is 341 nanometers. 341 nanometers, that is the threshold wavelength. The wavelength should not go above that. So it means this one will emit radiations because light is of wavelength between 320 to 550. That means 320 to 341 radiation can cause photoelectrons. I'll also check this one here. So I have 3 exponent 8 divided by 5.8 exponent 14. Then I change this to 1 exponent minus 9. So this one is about 520 nanometers threshold wavelength. So 520 is also within the range. It is less because they said the wavelength should not exceed a threshold. So 520 is the maximum. So between 320 to 520, this will also emit radiations. You can also check this one, or you can check the frequencies of each. You can check the corresponding frequencies. You get the frequency corresponding to 320 and the frequency corresponding to 550. And if the frequency is less than the threshold, if the frequency is greater than the threshold, it means the photoelectrons can be emitted. If the frequency is less than the threshold, photoelectrons are not emitted. Or you can check the work function by looking at the energy of the photons. You can get the energy correspond to this wavelength and energy correspond to this wavelength and see if the energy of the photons is greater than the work function, then a photoelectric emission is possible. If it's less, then it is not possible. For example, let me check. This is the work function. Let me find the energy range here. For 320, the energy is going to be equal to 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by 320 times 10 to the power of minus 9. So 6.63 exponent minus 34 times the 3 exponent 8 divided by 320 exponent minus 19. So this energy is, sorry, I said minus 19, it's minus 9. So this energy is, let me just repeat this, 6.63 exponent minus 34 divided by 3 exponent 8 divided by 320 exponent minus 9. So this is 6.2 times 10 to the power of minus 19 joules. That is the highest range. That is corresponding to 320. Then corresponding to 550, 6.63 exponent minus 34 times 3 exponent 8 divided by 550 exponent minus 9. So this is 3.6 times 10 to the power of minus 19 joules. So the energy of the photon must be greater than the work function for emission to be possible. So let's check 6.2. So this one is 3.8 times 10 to the power of minus 19. 3.8 is the work function, but 6.2 is above 3.8, so that one is possible. 5.8 is the work function, 6.2 is less than 6.2 is greater than 5.8. That means the energy of some photons is greater than 5.8, so that is possible. 9.0 is above 6.2, so this one is not going to be possible because the energy of the photons is less than the work function. Okay. For more information, you can check the solved past paper questions to see such a question. Then you can also try this one. So we're just using a simple formula. They've given you the wavelength. They've given the threshold voltage. So for each lady, calculate the experimental value for H, and hence determine the average value for the Planck's constant. So because you have the threshold voltage and you have the wavelength, you should be able to obtain the Planck's constant. So of course here just the energy HF, which is going to be hc divided by the wavelength, is simply going to be equal to E times V. So you can find H from lambda times E times V over C. So you can find H for each of the metals and obtain the average. I think this one is a direct question. I will not go through it. But remember, state which of the photons could cause the release of an electron from the metal. It is only photons whose energy is above the threshold frequency, is above the work function. So you have photon energies of this, and this. They strike a metal surface whose work function is this. So it's only photons whose energy is above the work function, which is 1.8, that will cause photoelectric emission. Okay. The table below shows the work function of several different metals. Which metal requires the highest frequency of electromagnetic waves to release electrons? So you look at which metal has the highest work function. And of course, that is 4.9. That means it would require the highest frequency. Because for emission to occur, frequency of the incident radiation should be greater than the threshold. The one with the highest threshold will require electromagnetic waves of higher frequency. Which metal will release electrons when the lowest frequency of electromagnetic waves is incident on it? So the one with the lowest threshold frequency will easily release electrons when lowest frequency of electromagnetic waves is incident on it. Then calculate the threshold frequency for zinc. So zinc has that work function, and the work function is equal to H times F naught. Remember, 1 electron volt is the same as 1.6 times 10 to the power of minus 19 joules. So you just use that to find the threshold frequency for zinc. What is the longest wavelength of electromagnetic waves that will release electrons from potassium? So when you look at potassium, it has this as the work function. It has this as the work function. By the way, the work functions are given both in joules and electron volts. So work function is equal to hc divided by lambda naught. So you want to find lambda naught as hc divided by the work function. So that will give us the longest wavelength for potassium. Electromagnetic waves of this wavelength are incident onto the surface. Work function is given. Calculate the energy of a single photon, that one is HF. The maximum kinetic energy released from the metal. Remember, HF is equal to work function plus the maximum kinetic energy. So you can just substitute. Then determine the speed of the emitted photoelectrons. The maximum kinetic energy is a half mv squared. So you can be able to get the speed. When electromagnetic radiation of wavelength 2000 nanometers is incident on a metal surface, the maximum kinetic energy of the electrons released is found to be 4.0 times 10 to the power of minus 20 joules. Then determine the work function. So they have given us wavelength, so H times F equals the work function plus the maximum kinetic energy. So since they gave us wavelength, we'll just say H C over wavelength equals to phi plus they gave us the maximum kinetic energy. So we just substitute in the equation and find phi. I think that should be the end of lesson 3. This was quite long, but
At 29 and I find myself wondering what did happen to the last 10. I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we need to set the rewind. And 19 was the year I had to leave you, but now I'm seeing all the signs. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this an answer. Maybe the biggest question was in the last chapter. You gave me the soul I have today. Without you I never could have moved away. But now I see what you teach. I do believe I always should have stayed. Yeah. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure. But one day I'll be yours again. One day I'll be life lessons come one in a dozen. The other 11 give something from nothing. Life lessons come one in a dozen. The other 11 give something from nothing. Life lessons come one in a dozen. The other 11 give something from nothing. Life changes, just open the door. One thing certain, I'll always be